Alright, welcome to simple harmonic motion and oscillations. This is going to be a really different chapter because while we are still dealing with things in motion, what it's doing is setting us up to learn about sound and light. We'll start sound in the next lecture for chapter 15, and we'll study light waves all next semester. And so understand that this is a transition from how things move to these very specific kinds of energy in the form of sound and light. But we are going to still focus on how things move. So there's a little bit of vocabulary that I'd like you to try and figure out in your book. Just go ahead and pause the video here. And I'm going to go on to give you the definitions that I want you to know as well. So an oscillation is any back and forth or repetitive motion with movement about a starting point. So something that has a starting point, it moves and it comes right back to that starting point, and then it does the same motion again. These things are characterized by having a period, which we represent with a variable t, and amplitude, which we'll talk about in just a second, and a frequency. And frequency and period are vocabulary words that you already know, even if you didn't like them back from uniform circular motion. My examples of oscillations are a record spinning and your leg walking, and so your leg has a starting position that it returns to and then kind of goes through the same motion over and over again. I'd like you to come up with 3 examples of your own that represent oscillations, something with a starting point, it moves away, and it comes back to that starting point over and over again. My examples are going to be the hands on a clock, a metronome, which is the little thing that keeps time for music, and monkeys swinging from a tree. So I'm just going to put monkey. There we go. Alright, and then simple harmonic motion is a specific type of oscillation whose velocity, acceleration, and amplitude, this big A is amplitude, can be described as a sine or a cosine graph. A sine graph, starts at a non-zero point and kind of oscillates, and then a cosine graph, the only difference is it starts at 0 and then oscillates. My example would be a bungee jumper. So a bungee jumper starts way up high and they spring down low and then back and forth, and so they would be described as a simple harmonic motion. Right? You see simple harmonic motion all the time in your daily lives. Waves washing up and back on a beach. The atmosphere does the same thing as waves and creates these little ripples. Deer jumping, they've got a certain frequency, it's repetitive, they come back to the same point. Tides coming in and out, there's high tide and low tide, and high tide and low tide, and it oscillates between those two. Pendulums of any sort, be they terrible or not. Drums, actually, the head of a drum, every time you hit it, has different modes that it resonates at or oscillates at. This picture will make a lot more sense next time when we talk about sound. But depending on where you hit a drum, it has different types of oscillations that it shows. And those are shown here in an idyllic manner. If you're shredding nar nar pow pow on a half pipe, that's an oscillation, right? This guy's going to come down and then right back up and down and back up. If you're bungee jumping, I don't know if any of you guys have ever been. I imagine it's horrifying. Swing sets are another really great example of an oscillation. The person goes back and forth and back and forth. Alright, hummingbird wings are another really good example. Repetitive motion going back and forth. That's a lot like your legs. Guitar strings, every time you pluck a guitar string, it kind of vibrates back and forth until it stops, and then microwaves are going to be my example I'll talk about a little bit later. So we're going to explore 3 types of oscillations. Those are going to be pendulums. And we've got 2 types. We'll explore simple and physical pendulums. We'll take a look at springs, or things that go boing like a bungee jumper. And then we'll also look at rotational motion, which is like my microwave. To play along, if you want to have kind of your own demonstrations at home, for the pendulum portion, you'll need some sort of a mass on a string. I keep my school keys on a lanyard, and so that'll work. For the spring, you can get a rubber band or a hair tie, and put your keys on that for that demonstration, and then a microwave for the rotational motion. Now, if you don't want to play along, you don't have to. I've got videos throughout the lecture that we'll take a look at. I'm going to start you out with your vocabulary and your formulas. These might not all make sense right now, but go ahead, pause the video, and take a second to write these down. So an oscillation is any type of repetitive motion. They all have a period t, which is the time it takes for one complete revolution. They have a frequency, which is the number of revolutions per second. I'm going to give you a new unit for this, and so Hz. Frequency is usually measured in hertz. 1 hertz is equal to something with a period of 1 second, which is s to the negative 1, right? And we've already explored this idea that frequency is equal to 1 over the period. The unit, because this is a really funny unit, we just call that a hertz, right? So something that has a period of 1 second, takes 1 second to go completely around, has a frequency of 1 hertz. Amplitude is the distance of the oscillation along the x-axis. This could also be along the y-axis, depending on what we're talking about. If it's a bungee jumper, they're obviously going up and down. And then SHM is an abbreviation I'm going to use throughout. And this is anything that follows a cosine or a sine function, right? Doesn't matter where it starts, but it just goes up and down. The same distance both ways, right? There's a few properties of simple harmonic motion that I'd like you to know. These are on page 458. The restoring force is linear, and we'll talk about that in just a second. Position, velocity, and acceleration are specified for a given amplitude and frequency, and I've got a lot of formulas for this one. Max speed and acceleration depend only on the amplitude. Amplitude and frequency are not the same thing, nor do they matter or vary the other one. They're not going to affect each other. And the total energy of a system is constant, oscillating between potential and kinetic energy. This one, there's a little exception to that because the real world doesn't work this way. But for our idealized models, that'll work. All right, so these are your simple harmonic motion formulas. I'd like you to go ahead, pause the video, write these down, and then we're going to go through them and kind of identify, well, which formulas are relevant to what concepts as we go through. So go ahead and take a minute and write these down in your notes. All right, and so for our first example, I've got a simple pendulum here, right? And this pendulum is swinging back and forth. And we could characterize it as simple harmonic motion. It's got a starting position, and it returns to that every so often. And so I'm going to put a little dashed line for the neutral ground of this pendulum, right? And I'm going to say, okay, this is its max on this side. This is its max on this side. And I'll call each of these 1 meter. And so for a position on the x, this will be like a -1, and this will be a +1 meters. And then it's got this 0 function right here, right? And so for the amplitude of this, it's this displacement from 0. And so the amplitude of this pendulum is going to be 1 meter, right? It's the distance that it travels in either direction. Amplitude is usually described as an absolute value, and so this oscillates between -1 and +1 meters. Now the period for this one is the time that it takes for one revolution. I can pick any starting point, right? I can choose here, here, or here. It doesn't matter, but either way, it's going to be the time that it takes to get back to that starting position. So I'm going to choose this one, and I'm going to count. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4. All right, and so that's going to be 4 seconds. And then its frequency is going to be 1 over the period, which is 4. And I know this is expressed in hertz, so this is going to be 0.25 Hz. Right? And it's just that simple. All right. I don't like this word magnitude. We're going to use the word amplitude. MP. Things can have different amplitudes, and so as you look at this, which one of these, the red line or the blue line, is going to have a greater amplitude? Well, it's going to be the one with the red line, because as I draw, you know, this is its 0 line, and this is its 0 line. the red one is traveling a much greater distance from 0 than the blue one, and so its amplitude is going to be larger. As far as frequency goes, right, frequency is the number of revolutions in 1 second. And so let's see, each one of these marks is 1 second. I'm going to extrapolate out to 5 seconds right here. I'm going to draw that line. And so it looks like this one does almost 1 revolution in 5 seconds. So let's see, this one has 1 revolution out here, right? And then while this one right here has a little more than 3 revolutions in a second. And so this would be like 1 over 0.75. And this would be like 1 over 3. And so this one, the blue line, has a much higher frequency, or no, I'm sorry, a much lower frequency than this one down here. All right. And so again, we can look at this in terms of like a pendulum motion or circular motion. Same thing applies, right? And so here, we've got a very low magnitude or very small amplitude and a very high amplitude, a very low frequency and a very high frequency in number of revolutions per second. So time for you to play. If you've got a pendulum at home, you can go ahead and do that. If you want to just watch along with my video, we're going to be answering these 3 questions for a pendulum. And then I want you to kind of experiment, okay, well, how can you change the period of a pendulum? Okay. And so if you've got your own pendulum at home, you can go ahead and answer your 3 questions. I've got a little video. And then figure out how you can change the period, the time it takes for 1 revolution, 1 out and back. All right. And so, let's see, I'm actually going to go back here. No. There we go. And so I've got the amplitude, the period, and the frequency. We already did this for my simple pendulum. What we're going to do is we're going to go along and answer that other question about, well, okay, how can you change the period of that frequency? All right, so I've got a little digital pendulum here, and I'm going to add my photo gate timer, which will tell me about the period of this pendulum. And I'm going to go ahead and pull my pendulum back, give it a little bit of an amplitude, right? And I'm going to start my pendulum timer here, and it's going to do the time it takes to do 1 revolution, right? And all the way back, and this pendulum has a period of 6.71 seconds. And so let's say, okay, I bet if I reduce the mass, it'll change the period of my pendulum, right? That first one was 6.7, so I'm going to start this one. Whoop. There we go. And nope, sure enough, that mass didn't change it. And so maybe if I try changing the length of that pendulum, let's say I'm going to shorten it up considerably. And so we'll go up to like half the length here. Right? Same angle that it's going through. We just want to change the period of it. And let's see if that did it. Yes, indeed. And so what I find through this little experiment is that the mass of whatever's on the pendulum doesn't really matter. What matters is the length of the pendulum in determining the period or the time for 1 oscillation to happen. When we take that and we look at your simple harmonic motion formulas for a pendulum, we can talk about the position that pendulum is in terms of its frequency and the given time that that pendulum has been swinging. We can talk about its velocity at any point in the swing as a function of its frequency and its amplitude, and again, its frequency and the time at which we're trying to find the velocity. We can also find the maximum velocity, which is this little component of that equation. It is the frequency times the amplitude times 2 pi, right? And we see that over here. Right? And then we can talk about its acceleration at any given point as a product of its frequency, its amplitude, its frequency and the time. We can also talk about max acceleration in terms of frequency and amplitude for that pendulum. In our little experiment, we decided that the longer the length, the shorter the period, and that makes sense mathematically because of these two equations. And then period and frequency are just kind of the inverse of each other, right? And so we can just flip everything, do the same calculations, and get the frequency or the period. All right. This is really cool because this is how seismometers work. Seismometers are measuring devices for earthquakes. And so we actually take a pendulum, and instead of swinging the pendulum, we put kind of paper underneath it, and this earthquake shakes it to and fro and to and fro. And we can measure the magnitude or the size of the earthquake based on the amplitude of the pendulum, or the amplitude of the paper against the pendulum. Right? Pretty cool little thing. So what we just talked about were simple pendulums. We're very briefly going to talk about physical pendulums. Simple pendulums don't happen a whole lot in real life. There's like grandfather clocks and swing sets and seismometers, and that's really about it, right? A physical pendulum is something that's much more likely. This is something where the length of the pendulum, like a leg, has mass distributed along it, not just like a string with mass at the end. Physical pendulums have a little bit different way of calculating period and frequency because of this whole mass distribution thing. And so this is kind of a fun experiment. Your leg has a natural frequency at which it swings. And so if you try and stand up and swing your leg back and forth, just really relax, don't even think about it, that's the natural frequency and period of your leg as a pendulum. You can make your leg have a different period or frequency, and so you could go for a faster period, which would give you a higher frequency. So try and swing your leg faster than it normally goes, and what you'll find is that you can do this, but it's really, really awkward and incredibly difficult for you to achieve anything other than your natural frequency. In running and walking, this is very apparent in our strides. And so running, you have a shorter period for the swing of your leg, right? You are making it go faster. Your body's normal balance system is such that if your right leg is going forward, then your left arm should be going forward as well. And then if your left leg is going forward, your right arm is going forward. It's kind of flip-flop. And that's just for balance of your body. To achieve this greater or this faster period when you're running, what you actually do is you shorten up the length of this pendulum so that your arms can have a faster period. If your arms have a faster period, then your legs can have a faster period as well, and you can still maintain balance. Another kind of funny experiment is try running with your arms fully extended, and it's incredibly difficult to do, just like this. Because your arms extended have a much different period than your arms when they are short. And so just like our other pendulum, anytime things get shorter, they get faster. In your simple harmonic motion formulas, you've got your physical pendulum frequencies down here. This is the mass of the pendulum, gravitational constant, usually Earth, right? And then D is the distance to the center of mass. And I, this is an old concept, but I is the moment of inertia. When we talked about moment of inertia and circular motion, you had that big page with all the formulas, and that's where you get this from, right? The big idea behind physical pendulums is the same idea behind normal ones, which is that if the center of mass is closer to the pivot, then the period is going to be faster, right? They can go through one revolution much, much faster. All right, so let's move on to springs. This is our other kind. If you're doing demos at home, this is when you get out the rubber band and the keys and you kind of wiggle them back and forth. Your book experiences or experiments with both vertical and horizontal pendulums, and so I've given you both of these, right? And for my pendulum or your pendulum at home, we're going to find the amplitude, the period, and the frequency of this pendulum. All right, now I'm going to use, let's see, I'll use the vertical pendulum, and I'll mark, all right, that's the top, and that's the bottom, and right in the middle is the normal spring constant. And so what happens is I can pull the spring down or push it up to start it past its neutral position, and let's say it's going a distance of 2 centimeters, 2 centimeters, right? And so this would be like a negative 2 centimeters, right? This would be like a positive 2 centimeters, and it's oscillating back and forth, and so its amplitude I can go ahead and say is 0.02 meters. Now the period of this oscillation, I'm going to count it from the top, right up here, is the time it takes for 1 revolution, right? And so I'll wait for it to get the top, and 1 Mississippi, 2 Mississippi, 3 Mississippi, 4. And so again, we've got a period of 4 seconds, which means my frequency is equal to 1 over the period, which is 1 over 4, and that's 0.25 hertz, right? And remember, amplitude is an absolute value. If I had done it over here, I could mark there and there with a middle part right there, and 0.02, 0.02, right? Just remembering that you can set up that coordinate plane, and 0 is always the neutral zone. Wherever your pendulum or whatever it is oscillating would hang, if there were no external forces, and the amplitude is the distance between the 0 mark and its high or its low, your choice. All right, and so for your spring, what's the period, what's the frequency, and what's the amplitude, and then how can I change the period of it? Well, to change the period of a spring, you probably want to say that it depends on the amount that I pull this down or push it up, and then that'll make a difference. Well, no, not really. When we look at the formulas, right, down here, the frequency and the period for springs, the only 2 things that matter are the spring constant and the mass that I hang from that spring. Right? And those are the only 2 things that'll change the period and frequency for springs. I can still talk about the position of the spring, the velocity of the spring, and the acceleration of whatever's on the spring. Or I can also talk about the maximum velocity and the maximum acceleration for that spring. No problem. Alright, and then last but not least, we've got rotational motion, and this one is interesting, but it's not as intuitive as, you know, pendulums and springs, because, well, where the heck is the starting position, right? It's not something that swings back and forth and kind of has this neutral ground. This is a top view of rotational motion, and this is a side view of rotational motion. And so what is the period, what is the frequency, and what is the amplitude? If you're following along at home, I told you that you needed a microwave, and you can probably guess where I'm going. If we view this from the top, this particular drawing is going in a counterclockwise motion, right? And my microwave does the same thing. And when I look at it from the top, it doesn't make a whole lot of sense why this is simple harmonic motion. But if I look at it from the side, what I'm going to see is that this cup goes back and forth and back and forth and back and forth, just like our horizontal spring. And so this is simple harmonic motion. And so I've got a little video. We'll answer these questions. If you want to use your own microwave, that's fine. And then how can I change the period of this thing? All right. So let's see. I've got my little video, and we'll mark the center point at the front as the starting position. And we need to answer amplitude, period, and frequency. All right. So let's go. Alright, so 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, and 6 Mississippi. Great. Okay, so I've got a period of 6 Mississippis. There we go. And so my period equals 6 seconds. I know that my frequency is equal to 1 over the period, and so this will be 1 over 6, which rounds to 0.17 hertz. Okay. And then the amplitude is pretty interesting. The amplitude is just the radius of whatever circle I'm working with. And then, okay, well, how do I decrease the time for the period, the time for 1 revolution? And you might want to initially say, okay, well, I changed the amplitude, but you don't. Remember, amplitude and frequency are not related. And so the only way that I can change the period or the frequency of this thing is just to make it spin faster, right? If that's a record player, then I up the revolutions per second, right? And make my record sound like chipmunks. Or if I want to slow it down, then I just slow the number of revolutions per second, and my record will sound normal, right? And so, again, when we're talking about these things, I can still talk about the position, velocity, and acceleration for things in circular motion. I can talk about the maximum velocity and the maximum acceleration. The only reason I have a maximum velocity and a maximum acceleration for this one is that, well, the direction is changing, right? It's got a constant angular velocity and a constant angular acceleration, but because it's changing directions, then these will change as well, and I can do that as a function of the frequency and the amplitude, just like I've done for everything else. Okay? This is all well and good, this whole simple harmonic motion thing, but in real life, oscillations aren't sustained, right? If I pull a spring, what actually happens? Well, I pull it, and it bounces a couple times, and then it comes to rest, right? And so I can pull that spring, it's got a lot of initial energy, and then it kind of pitters out, right? If you throw a ball on the floor, the same thing happens. If you push somebody on a swing only once, the same thing happens. And so, well, why does this happen? Right? It's usually as a result of friction in that system. Things are lost as heat energy from that friction, and we know from the previous chapters that heat energy is not really lost energy, but it's changed into a form that we can't use. Right? We call these things damped oscillations, and instead of this kind of idealized version of an oscillation that we've been talking about, damped oscillations or real kind of oscillations look a lot more like this. They have this initial kind of spike, and then they pitter on out. One of my favorite examples of this is the doorstop, right? This is a damped oscillation that you can hear as well. All things have a natural frequency at which they resonate, and so when I'm walking through my house and I trip on the doorstop, right, it oscillates, and then it kind of pitters out. We have this idea of damped oscillations. If there's something in our world, though, that we want to have kind of a perfect oscillation for, we say that we have to drive the frequency. And so this means that we have some kind of external pushing power, right? And this external pushing power kind of drives the oscillation and keeps it going and keeps it from pittering out. This really interesting thing happens that if my driving oscillation is equal to the natural frequency of whatever that is, the amplitude of that oscillation actually increases. And so I've got a good example of a swing set for you. Alright, so swing sets are a really great example of driving frequencies. Swing set is it's a natural, simple pendulum, right? I've got a mass on the end of a string of length, whatever. And just like your leg, right, this has a kind of normal frequency that it likes to be at. And that's its max capable amplitude and period. And anything outside of this is just kind of awkward and not easy to achieve, right? And so swing sets, though, if I only give one push, it pitters out and it becomes a damped oscillation. So I really need a driving force. And so what I find is that if I push at the natural frequency, right, when the person gets to the back, then I achieve this really great kind of amplitude, this really big amplitude for that natural frequency. So there's the natural frequency of the pendulum. This person is pushing at that natural frequency, right? And what that leads us to is a really, really big amplitude for that system. You've probably experienced this as a trampoline super bounce, right? Whenever you're on a trampoline, like every 10-year-old knows this, there's this whole circle that you're jumping in, and if you hit it at just the right spot, you get this super bounce, right? Which is that the frequency of your jumps are equal to the natural frequency or the resonant frequency of the trampoline, and then you get this really big amplitude as a result of that. I also want to play a video about driving out of frequency, and so this is an example of when the driving frequency or the external frequency does not equal the natural frequency, and we'll get an idea of kind of what happens there. All right, it makes for a very uncomfortable swing ride. Nothing really happens to the amplitude. In fact, it kind of hinders the amplitude as compared to the other one, right? And so if that driving frequency is out of sync, what we see is actually a decreased amplitude. Okay. I'm going to talk about these. I'm going to give a couple of vocabulary. I'm going to give a couple of vocabulary words to that idea, which are constructive and destructive interference. And so when the natural frequency is the same as the driving frequency, we get kind of an addition of those two amplitudes and a increases, right? But if F naught, the natural frequency, and the external frequency, right, like the guy pushing, are kind of out of sync, right, and they don't match up, then what we actually get is destructive interference, or kind of a destruction of the amplitude. The amplitude actually goes down, right? The idea of this whole natural frequency equaling the external frequency or the driving frequency is called resonance. Every object in our world has resonance. Everything has a normal frequency at which it would kind of oscillate if given the chance to. You probably know this, like I said, as the trampoline super bounce, right? And wine glass music. And so wine glass music is pretty fun. As you put different levels of water in a wine glass and you kind of spin your finger around the edge of the wine glass, they make different noises. And those noises are based on the frequency at which that glass is oscillating. As that glass oscillates and kind of moves back and forth at an atomic level, moves particles in the air back and forth at different speeds or different frequencies, and you get different sounds. And so high frequency sounds are the same as high pitched sounds, and low frequency sounds are the same as low pitched sounds. If you fill a wine glass all the way up towards the top, you get a much higher frequency, and if you have it very low, you get a low frequency due to the mass. It's kind of like a spring oscillation. There's a couple really cool examples of real-world resonance that I'm going to show you. Towers falling in earthquakes, and so buildings have a natural frequency. Suspension bridges have a natural frequency. Crystal has a natural frequency, and tides have a natural frequency. And so I'm going to show you little brief videos about all of those. Alright, and so here we've got a kind of a makeshift earthquake, and we've got buildings of different heights, buildings, quote unquote. And what's going to happen is this earthquake machine right here is going to oscillate at different frequencies. And what we'll find is that as the driving frequency equals the resonant frequency of each building, the amplitude increases dramatically. And so as this begins to increase, we start to see an amplitude increase in the very, very tall building, right, with a long pendulum, low frequency. And as it continues, this will kind of get out of control for this building. And we'll see that as you go beyond this, as you go beyond the resonant frequency of that first building, the amplitude kind of decreases again. It gets back under control. Alright, and then it's going to move beyond the natural frequency of that building, The amplitude calms back down, but oh no, it's approaching the frequency of the middle building, and so we'll see that amplitude increase greatly. This is how buildings fall down in earthquakes, right? That their resonant frequencies are matched, they're equaled. And then it goes beyond the frequency of this one to go on and vibrate the small one. Right, this is another good example of resonant frequencies being equaled, and this is by earthquakes. What we find is that this bridge has its own natural frequency as the ground begins to shake and winds. I don't remember if this was winds or an earthquake. I think maybe it was winds. As it begins to resonate at its natural frequency, then what we find is that the amplitude actually increases. In this case, the bridge went on to break, right? Because those amplitudes kind of stressed its structure so much that it actually broke. No, you can see that one car. Alright, and this is one of my favorites. It kind of goes along with the whole wine glass thing. This wine glass has a natural frequency. Remember, high frequency equals high pitch. And so what the singer is going to do is actually kind of vibrate the air particles back and forth at a frequency, and she's going to match the wine glass. Once that happens, the amplitudes increase dramatically to a point that the structure can no longer sustain it. And I love it that you actually see her kind of thump the wine glass to figure out, okay, what is the resonant frequency of this thing? I can hear that and I can match that sound. The Bay of Fundy is a tidal example. So tides are waves that move across the world as a result of gravity and the moon and the sun. I won't get into all that. But this is a place where the orbit of the Earth around the sun and moon, as well as the spin of the Earth, actually match up with the tidal cycles. And what it does is it increases the amplitude and creates really, really drastic tides at this place. And so this is a time-lapse video. You see tides coming in. These are boats at a dock here. Notice they're completely on dry ground at this point. As the tides come in, we see the amplitude increasing. Amplitudes at the Bay of Fundy can vary by as much as 24 feet from high tide to low tide, and that's huge. But again, because the driving frequency is equal to the resonant frequency of the tides, we get these really big amplitudes. It's a port where ships come in and unload as well, and so this is kind of funny. They see cargo ships, it takes a long time to unload them, and what they do is they will actually miss the tide and be stranded on completely dry ground and have to wait for the next high tide to come back in. Alright, and let's see, I'm going to go on to talk about my last example of resonance and resonance structures. And that is the way you hear, right? The way you've been listening to this whole video has to do with the natural frequency of your inner ear. Inside of your ear, there is this little structure called a cochlea. On your cochlea are your hearing nerves, and they attach throughout all different points of this little structure. What happens is that sound waves will come into your ear. They resonate your eardrum, and it kind of carries those frequencies into your cochlea, and depending on the part of that will resonate at its resonant frequency as well. Your nerve picks it up and determines a pitch, right? what we see is that the very, very low parts of your ear, or kind of low frequency noises, actually resonate in the very, very inner coils of the cochlea, whereas the really high frequency noises resonate on the outer coils of the cochlea. And remember, you can kind of have nerves at each point. As these things resonate and move kind of back and forth and back and forth, that nerve gets excited and says, oh, I've got a noise, and sends that to your brain as a pitch, right? And kind of determines what pitch you hear. Pianos work the same way, and so this is just an idea of kind of where pianos fall. 500 hertz, which is middle B on a piano, resonates right about there, right? With the lower noises being in here and the higher pitched noises being out here, right? This leads us to a really interesting thing that I'm kind of fascinated by, which is cochlear implants. For people who have genetic disorders of the cochlea, what we can do is actually create a surgery where this eardrum is damaged. It doesn't send the signals. And what we can do is attach this external microphone to their head, have a little wire that goes down and kind of stimulates the cochlea at different points so that signals can be sent to the brain. Sound is captured by the microphone. A harmony sensor kind of digitizes it and sends it to the cochlear implant. Then the cochlear implant, just like a normal cochlea, kind of resonates at different frequencies and is attached to that hearing nerve, and then the hearing nerve sends those signals to the brain. We see these becoming increasingly popular, and people get the experience of hearing for the first time because of this kind of resonance technology. Very cool. And so this is actually pretty cool. This is a little kid named Cooper who has recently received surgery and a cochlear implant. And this is them turning it on for the first time. And this is Cooper hearing for the first time because he now has a new resonant structure in his inner ear.
Hi. Yeah. Do you hear something? Hi. Oh, keep on. It's on. Not anymore. Keep it on. Uh-oh. Alright, so right now I'm going to drop him down since he did respond to that. Okay. Hey, good job. Back on. I know. Hi, Cooper. Hi, Cooper. Hi, Cooper.
Alright, and on that I'm going to leave you with your homework problems. You do have some conceptual problems as well as some quantitative problems. And for the quantitative ones, just use those formulas that we jotted down earlier. And if you've got questions, bring them to class. I'm excited to hear them.